Hello everyone, my name is Varad Daoo and I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. I welcome you all to this 8th lecture of structure of atom. So in the previous class, what we have seen? We have seen that there are two kinds of atomic spectra. One is the absorption spectra, another is the emission spectra. We studied about how both of these are calculated, and we also studied that both of these are complementary to each other. That is, if we study the information conveyed by either one of them is the same, then further we studied the emission spectra of hydrogen atom, and then we established that the lines which we observe in the spectrum of hydrogen atom, we defined it or categorized it into five series of lines. These are Lyman series, Balmer series, Paschen series, Brackett series, and Fund series. We also saw about the Red-Bunk equation, right? And we saw the three variants of this equation. One for the pure hydrogen atom, for Balmer series. Then we generalized it for hydrogen atom to any series, and the last one, which is the most general one, we found out by we established that for hydrogen-like species, right? Like lithium plus helium plus two, like these ions. Then we solved some examples, and at the end we established sort of touched the drawbacks of Rutherford models and a need for a new model for atom. There we concluded saying that this new model is the Bose model given by Niels Bohr. Right. So in this class, we are going to study about in detail about these drawbacks, and then we are going to study the Bohr's model of atom. Right. Let me write down lecture 7, structure of atom. The first topic which we are going to study is drawbacks of Rutherford model. So according to Rutherford model, an atom consists of a heavy positively charged nucleus surrounded by negative charged electrons, right? Moving around. So according to Rutherford, as a recap, so according to Rutherford, what we had is this is the nucleus and electrons are revolving around it. Let's say these are the electrons. This is the nucleus, and electrons are revolving around it in the form of these circles, right? Let me write this down. The different color. These are electrons, right? And these are nucleus. And according to that, it is revolving. This is the nucleus, right? So accordingly, in this model, the electrons were revolving around the nucleus in this direction, right? So according to the first model, an atom consists of a heavy charged nucleus. So this is the heavy charged nucleus surrounded by negatively charged electrons moving around in a circular path called as orbit. So this is called as orbit, right? This model was analogous to the solar system, right? Where the nucleus may be compared to the sun and the electrons to the planets. The Coulombic force between the nucleus and the electron is, right? The Coulombic force between electrons and nucleons is, let's say, electrostatic force. Let me write this down with a different color, right? The force between nucleus and electron, that is the electrostatic force, is K Q1 Q2 by R square, where Q1 Q2 are the charges and R is the distance of separation between the molecules and the electrons, and K is the proportionality constant. So this is similar to the gravitational force acting between the planet and sun, which is G into M1 M2 by R square, where G is the gravitational constant and G is the gravitational constant, M1 M2 are the mass of the species, and R is the distance of separation between the planets and the sun. However, there is an important difference between the solar system and the nuclear model, right? The electrons have extremely small mass and are negatively charged, whereas planets are massive and neutral. The planets revolve around the sun in well-defined circular path, right? However, there arises a difficulty with Rutherford's model. It failed in the light of electromagnetic principle, right? So what we can write is, so we will discuss it. Right? Rutherford's model failed in the light of electromagnetic radiations, electromagnetic principles, right? So we will study about it. It was shown by Maxwell that a charged body moving under the influence of attractive forces loses energy continuously in the form of electromagnetic radiation, right? Thus, unlike a planet, the electron is a charged. Thus, unlike a planet, the electron is a charged body, and it should emit radiations while revolving around the nucleus. As a result of this, the electron should lose energy at every turn and move closer and closer to the nucleus. Right? So let me write this down, and then we will discuss about it. So what Maxwell showed? Maxwell showed that when a charged particle is moving under the influence of other charged particle, the certain amount of radiation has to be emitted, because of which the energy of that particle has to decrease, right? Or radiation has to decrease, right? So what we can write, it was shown by Clerk Maxwell that a charged body moving under the influence of attractive forces loses energy continuously in the form of electromagnetic radiation. Thus, what we can assume this is, what we can conclude from this is, the electrons is a charged body and it should emit radiations, right, while revolving around the nucleus. As a result of this, what should happen is the electron should collide onto the nucleus, right? So I will show you the picture. As a result of this, the electron should lose energy at every turn and move closer and closer to the nucleus, right? Following a spiral path. Right? So it should be like this. Right? So electrons, as per this theory, both electron is a negatively charged particle, whereas nucleus is positively charged because of the presence of protons, right? So this is so electron is under the influence of attractive forces, right? Because we know unlike charges attract each other, right? So as per Clerk Maxwell, what he showed, when this electron is under the influence of attractive force, this electron should not have this electron should radiate emission, and we know that energy is nothing but h nu by lambda, that is hc by lambda or h nu, right? Energy is h into nu, which is hc by lambda. As this energy is associated with the frequency, losing the energy should result in losing of frequency, right? Decreasing frequency. So hence, because the radiations are being emitted, so those radiations should will have certain amount of energy, and that energy will come from the initial energy of electron. Hence, instead of this electron moving in a circular orbit like this, because some amount of energy has been removed in the form of radiation, let's say this is the radiations, right? Because of this radiation, the energy of its electron continuously decreases, and hence it cannot follow the circular path, but instead it should follow a spiral path. And ultimately what should happen is, ultimately this electron should collapse onto the nucleus, and thus making atom unstable, right? So this is gradual decrease in the distance between the electrons and the nucleus. So this was the main issue with the Rutherford's model, right? Consequently, the orbit will become smaller. So the orbit will become smaller and smaller, right? An electron would fall in the nucleus. In other words, the atom should collapse. The calculations have shown that it should take only about 10 raised to power minus 8. So time required for this should be around should have been around 10 raised to power minus 8 seconds for electron to spiral into the nucleus. However, this never happens, right? Because we know that at the end of the day, the atom is stable, right? Therefore, Rutherford model cannot explain the stability of an atom if the motion of electron is described on the basis of classical mechanics and electromagnetic theory, right? So obviously we may think that if the motion of electron in orbit leads to instability of atom, then why not consider the electron as stationary around the nucleus? So instead of this, we can just consider that a natural thought comes to our mind is if this moving theory is not able to explain the behavior, we should just be able to see that we can just assume that the electron is stationary around the nucleus. However, that is also not true. Why? Because if the electrons were stationary, the electrostatic attractive force between the nucleus and the electrons would pull electrons towards the nucleus, right? To form a model described by Thomson model, right? As per Thomson's model, what we had is we had an electron positively charged, uniformly distributed with electrons embedded into it, right? So both of these things could not be true, right? Hence, Rutherford's model also explained that the existence of certain definite lines in a hydrogen spectrum, right? It could not also explain the uh, the certain lines in the hydrogen spectra, right? So one is what we have seen. The other drawback is Rutherford's model could not explain or failed to explain the existence of certain definite lines in the hydrogen spectrum, right? If the electrons were to lose energy continuously, as discussed, right? Just now we discussed the atomic spectrum of hydrogen should have been continuous. However, the spectrum of hydrogen we already know has been found out to be discontinuous in the form of characteristic lines of different definite wavelengths, right? If the electrons were to lose energy continuously, as right, the atomic spectrum of hydrogen, the hydrogen spectrum of hydrogen should have been continuous, right? However, we know that that is not true, right? However, the spectrum of hydrogen has been found out to be discontinuous, right? Hence, Rutherford model could not explain this behavior. Hence, a new theory was required, and this theory was given by Niels Bohr, and it is called as the Bohr's model of atom, right? So that is what we are going to study next. Bohr's model of atom. Right? To overcome the drawbacks of Rutherford model of an atom and to explain the line spectrum of hydrogen, Niels Bohr, right? So this was given by Niels Bohr in 1913, proposed a model of atom which was based upon Planck's quantum theory of radiation, right? And the new model is called as Bohr's model of atom, right? So to overcome the drawbacks of Rutherford's model of atom, and to explain the line spectrum or the discontinuous line spectrum of hydrogen, right? Niels Bohr in 1913 proposed a model of atom which was based on Planck's quantum theory of radiation, right? Which is what we are going to study, right? So we are going to study the postulates of Bohr's atom or Bohr's theory or model, right? The first postulate was an atom consists of a small, heavy, positively charged nucleus in the center, surrounded by electrons, right? And electrons in an atom revolve around the nucleus only in certain selected circular paths, right? So it's not that the all electrons can occupy all the energy levels. There are energy levels, and electrons of only one energy level can translocate or can go to the larger energy level only if there is sufficient energy. So let me write this down. Right? The electrons, the sub postulate of this is that the electrons in an atom revolve around the nucleus only in certain selected circular paths. So this is very important. It cannot have all the energy levels, right? Which have fixed value, radius and energy, right? Fixed value of radius and energy, right? So this is very important. Fixed value of radius and energy, right? And these parts are called as circular paths are called as orbits. And these orbits are associated with the well-defined energies and are called as energy shells or energy levels, right? So these are numbered as 1, 2, 3, 4 and etc., right? From the nucleus or alternatively K11. So I will show you the figure, but before that, these paths are called as orbits, and these orbits are associated with definite energies and are called as energy shells, energy levels, right? Right, and these are numbered as 1, 2, 3, 4. So in order to understand this, let me drag a picture. Okay. So this is right. So as per what was the problem with Rutherford? With Rutherford, we had that electrons should continuously lose energy and finally collapse onto the nucleus, right? But as per Bohr models, the electrons, they do revolve around the nucleus and they do follow a circular path. However, the energy levels are not continuous. That means an electron, let's say this is an electron, right? So it is moving, let's say this is an electron, this is right. This is an electron moving in this orbit, right? Like this, in this direction. So it cannot occupy this energy level, right? Or it cannot occupy this energy level. There is no path between these two. There is a gap between these two, right? It can only, from this energy level, it can only jump to this energy level, right? It can only jump to this energy level. There is nothing in between like this, right? So because of this, what we know, what we have is electrons does not continuously lose energy, right? As per the electromagnetic radiation, and which was the problem with the Rutherford's model, right? Let us move on to the next page, right? Then the second postulate, right, was that the energy of an electron in the orbit does not change with time. So this is also very important. So the second postulate, the energy of an electron, right, in the orbit does not change with time, right? This is very important. So from this, what we see is if the electron is at this position, right, is at this position, irrespective of the time, the energy when it is revolving in this orbit is going to remain same. Let's say the energy is C1. So irrespective of whether time is t is equal to 1 or time t is equal to 2 or time t equal to infinity, the energy of this electron is going to remain the same. Hence, we can say that it maintains its orbit in this way, right? That is the main reason, right? So in other words, as long as the electron remains in a particular orbit, it does not lose or gains energies, right? This means that the energy of electron in a particular energy shell remains constant, Therefore, these orbits are also called as stationary states or allowed energy states, right? And the term stationary does not mean that electron is stationary, but it means that the energy of electron does not change with time, right? And this accounts for the stability of an atom, right? Let me write this down. So the subpoint of this is the first subpoint is, in other words, as long as the electrons remain in a particular orbit, it does not lose or gain energy. So this is very important. It does not, right? What does this mean? This means that the energy of the electron in a particular energy shell remains constant. Okay? So this is important. Hence, what we say is that therefore these orbits are also called as stationary states or allowed energy states, right? And the point which is to be noted here is that the term stationary does not, let me write this down, with does not mean that the electrons are stationary, but it means that the energy of the electron does not change with time, right? This accounts for the stability of atom, right? So the third postulate of this theory is only those orbits are permitted in which the angular momentum of the electron is a whole number multiple of a quantity, right? Only those orbits are permitted in which the angular momentum of the electron is a whole number multiple of a quantity which we call is h by 2 pi, where h is the Planck's constant and pi is the normal pi with a value of 3.14. This is also called as h cross, right? Now, why is this? So, an electron, like any other moving body, is moving in a circular orbit, has an angular momentum, right? So, and what is the formula for angular momentum? It will be nothing but linear momentum multiplied by the distance, that is mv into r, right? Where m is the mass of electron moving with the velocity v and r is the radius of the Bohr orbit, right? Thus, according to Bohr, the angular momentum is a whole has to be whole number multiple of this h by 2 pi or h cross by 2 pi. So this postulate therefore introduces the concept of quantization of angular momentum, right? So the sub point of this is the electron like any other moving body moving in a circular orbit has an angular momentum equal to, so the it will be mvr, where m is the m equal to mass of electron, p is the velocity of electron, and r is the radius of orbit, right? So as per this postulate, what we have is we should have this mvr has to be some n times, where n is a whole number, multiplied by h by 2 pi, right? Right. So in other words, this postulate introduces the concept of quantization. So quantization means uh, limited. Quantization means conservation, right? Quantization means conservation. Quantization of angular momentum, right? Hmm. And then the fourth observation, the fourth postulate is the energy is emitted or absorbed only when the electron jumps from one energy level to another, right? The energy is emitted or absorbed only when the electrons jump, right? Electron jumps from one energy level to another. So when energy is supplied to an atom, its electron absorbs one or more quanta of energy and jumps to the higher energy level, right? So this higher energy state of an electron is called as its excited state, right? The higher energy state of electron is called as excitation state. Excitation state, right? For example, let me drag a figure. So let us consider this as a figure, right? So right, when electron absorbs, so let's say this is the, so for A, whether the figure explains the energy changes in an electron jump, right? So let us say this is the initial position of electron and the energy at this point is E1, right? Let's say this is E1 and this is E2, right? So clearly E2 is greater in energy, right? So magnitude of E2, right? E2 has a higher, E2 is at a higher energy level than E1, right? So whenever this electron has to go from this orbit to this orbit, it has to absorb energy, right? And the absorb energy will be equal to what? This E2, energy of this level minus energy of this level, right? So energy absorbed will be E2 minus E1, right? And this state in this case would be called as a excited state, right? Because this is the original state, right? So this is called as excited state, right? And when the electron once left, now electron has gone from this shell to this shell, and now it is excited. So now electron can come back to this state again to its original position only when it emits a radiation which has an energy equal to E2 minus E1 and it loses this E2 amount of energy, right? So this is an energy E2, this is an energy E1. So it will emit the radiation, right? So this says this is a radiation. So this is basically absorbed radiation. Radiation absorbed, right? And this is radiation emitted, right? So when it goes from there, so energy absorbed, energy emitted will be E2 minus E1, right? Or you can remove the mod signature, right? So here also we have mod E2 greater than mod E1, right? So when electron absorb energy equal to E2 minus E1, it jumps to a higher energy level. And when electron jumps back to lower energy level, it radiates the same amount of energy, right? And this amount of energy emitted or absorbed is given by the difference of energy between these two energy levels, right? E2 minus E1, where E1 and E2 are the energy levels of those particular orbits, right? This means that the emission and absorption of energy occurs only in discrete value, right? Which is equal to the difference in two energy levels, right? So in other words, the energy of electron cannot change gradually and continuously, but changes abruptly as the electron jumps from one energy level to another and not in any value, right? And this explains the fact that atomic spectra are discontinuous, right? So let us write this down, right? This means that the emission or absorption of energy, right, occur only in discrete value, right? So in other words, what we can say is, so in other words, the energy of electron cannot abruptly right abruptly, but as the cannot change, cannot change gradually, right? Sorry, cannot change electron cannot change gradually and continuously, right? But changes abruptly, right? As the electron jumps from one energy level to other, and not in any value, right? Right? And this explains the atomic spectra. This explains the fact that atomic spectra are discontinuous, right? Right? And now let us discuss about the successes of Bohr's model. So based on these uh, postulates, the model which was proposed by Bohr and how it could explain some of the unexplained things, right? Right. So success of Bohr's model, right? Success of Bohr's model. The first success which we see is Bohr's atomic model explained the stability of atom, right? Bohr's atomic model explained the stability of atom. So according to Bohr model, an electron revolving in a particular orbit cannot lose energy, right? And therefore, the emission of irradiation is not possible as long as the electrons remain in one of its energy level, and hence there is no cause of instability in his model, right? The second one is Bohr's concept of atom explained successfully the atomic spectrum of hydrogen atom, right? Bohr's concept of atom explained successfully the atomic spectrum of hydrogen atom, right? So from the Bohr's model or atomic model, it is clear that the electrons can have only certain definite energy levels, right? When electron is present as close to nucleus as possible, the atom has the minimum possible energy and is said to be in ground state, right? For example, in the case of hydrogen atom, there is only one electron, and this should mean that electron is present at the lowest energy level, that is closest to the nucleus, that is with n is equal to 1, and this represents the ground state for hydrogen atom, right? When energy from one when energy from some outside source is supplied to it, it can absorb a definite amount of energy and jump to higher energy state, right? Such a state of an atom in which the atom possesses more energy than possessed in the ground state is, we already know, is called as an excited state, right? Thus, for hydrogen atom, first energy level, which is n equal to 1, is called ground state, and higher energy level with n value greater than 2 are called as excited state, right? This excited state is unstable, right? And the electron tends to come back to a lower energy level. And this transition, right, that is change from upper to lower energy level, occurs with a jump, and energy is emitted in the form of quantum equal to difference in energies between the two levels, right? In order to understand this, let us drag an image, right? So let's say, right, this is the ground state energy, right, and this is the excited state energy, right? So the quantum of radiation which is coming out, the energy only, we know that energy is only absorbed or emitted in the form of uh, discrete values, right? So when this quantum of energy, right, so this excited state is unstable, and the electron tends to come back to its original position, right, like lower energy value. And this transition, that is change from upper to lower energy level, occurs with a jump, and energy is emitted in the form of radiation, right? So this is the form of radiation, right? In the form of radiation. For example, if electron comes back from this energy state to this energy state, the energy level difference will be E2 minus E1, which is nothing but the energy of the associated wave, which is h into nu, right? The energy would be given by h into nu. Therefore, the frequency of the emitted radiation would be given by how? Right? So this is nothing but energy, right? Yes, which is nothing but E2 minus E1, which implies mu is nothing but E2 minus E1 divided by h, right? And since E1 and E2 can have only definite values for an atom, hence we will also have fixed value, right? Because this E1 and E2 are fixed. We know that these energy levels like this are not possible, right? Only this energy level and this energy level is possible, right? Hence the amount of energy released will also be some discrete value, and hence the frequency will also be a discrete value, right? Moreover, the energies of different energy level are characteristics of atom, right? So for example, so let's say this is a hydrogen atom. So for E1 and E2 for hydrogen atom will be different than E1 and E2 of helium atom or any other atom, right? So this is to be mentioned in here that E1 and E2 are characteristics of atom under consideration. Right? Hence, we see different atomic spectra for different materials, right? Therefore, the emitted frequency will also be the characteristics of atom, right? Right. So let us do some mathematics, right? So now we know that this mu will be nothing but E2 minus E1, E2 minus E1 by h, right? Right? Where mu is nothing but c by lambda, right? As mu into lambda is nothing but c, and c is the velocity of light in vacuum, right? Thus, c by lambda is nothing but E2 minus E1 by h, or lambda is nothing but hc by E2 minus E1. Since h and c, right, this h and c are constant, and E2 minus E1 corresponds to definite energy. Thus, each transition from one level to another will produce a light of definite wavelength, right? Let us write down. And this is observed as a line in the spectrum of hydrogen atom, right? Since h and c in above equation are constant, right? And E2 minus E1 corresponds to definite energy, right? Right. Thus, each transition from one level to the other will produce a light of definite wavelength, right? And this is observed as a line in the spectrum of hydrogen atom, right? Right? Now, if the electron jumps from, let's say, now, let's say, for example, here is the figure. Now, if electron jumps down from third energy level to first energy level, right? Having an energy, so this energy of this level is E3, energy of this level is E1, and then the wavelength of this line, right? The wavelength of the emitted radiation would be what? It would be lambda will be what? E3 minus E1 divided by H, right? Let's say lambda dash. This is lambda dash, right? Similarly, if the energy would have been E3, E5 to E3, E5 to E1, then energy would have been, let's say lambda double dash would have been E5 minus E1 divided by H, right? Thus, the different spectral lines in the spectrum of atom corresponds to different transition of electrons from higher energy levels to lower energy levels, right? Thus, different spectral lines in the spectrum of atom corresponds to different transition of electrons from higher energy levels to lower energy levels, right? Right? Simultaneously, now this we talked only for a case of one electron. Imagine if there would have been many electrons, right? So in that case, there would be many spectral lines, right? Simultaneously, appearance of large number of lines in the spectrum of hydrogen could be explained by, let's say this is a heading, simultaneous appearance of a large number of lines in the spectrum of hydrogen, right? Right? So this behavior is quite curious, right? And this is what this you can understand by a presence of many electrons, right? So this so we conclude our lecture here. So in this class, what we have seen is, so in this class we have seen about drawbacks of Rutherford's model, right? Then we studied about Bohr's model, postulates of Bohr model, right? Postulates of Bohr's model, right? Further we studied advantages or how it could overcome the drawbacks of Rutherford's model, right? right? How it could explain the explanation for stability of atom and explanation of emission spectra of hydrogen atom, right? Right? So I thank you all for attending this class, and I hope to see you again in the next class. So what we are going to study in the next class is we are going to study about the different the explanation for the different series, different lines, right? So we had in the previous class studied about Lyman line, Barman line, right? So we are going to study the explanation for those type of lines from Bohr's model, and then further we are going to study about the further we are going to solve some solved examples, right? And then we are also going to study about Bohr's radius and what would be the amount of energy of each orbital. So how what is the expression for that? That is what we are going to study in the next class, which will be followed by a couple of questions, right? So again, I thank you all for attending this class, and I hope to see you again in the next class, right? Thank you.